Hello everyone, I'm Weimar and I'm from University of Luxembourg. Today I will present our work MuDelta data-oriented mutation testing at commit time. This work targeted to rank and pick up top key random mutants in the regression testing. Mutation testing has been shown to be one of the strongest software test criteria. We have one program and then randomly change the program to correct a lot of mutants. These mutants are different versions of the program, and then tester executes the test or do test generation to kill these mutants. We can get the mutation score to indicate the test quality. According to the mutation score, we can refine the test suit quality and generate a new test to kill more mutants. Modern software systems are changed frequently, typically in continuous integration environment. However, mutation testing is time costly. Our study tried to apply the mutation testing in continuous integration by targeting a small set of mutants. In regression testing, to test the code change, we use some test metrics such as statement coverage or branch coverage. And when the test requirements are satisfied, for example, are their error part covered, we stop the regression testing. However, it cannot guarantee anything except the changed lines are covered. The common coverage metrics cannot test the effect of the change. Therefore, to estimate if the current test suit tests the change well, we need a new mutation testing formulation in which mutants can be found based on their relevancy to the change in the software system. Our previous work proposed a new concept, commit-aware mutation testing. In this involving mutation testing approach, the set of mutants change with each new commit. Through these evolved mutants, we can test the commit change better. We have the pre-commit variant and program, and then the developer submit one commit. We get the post-commit variant, and then we correct the mutants. The commit relevant mutants can capture the interaction between the commit change and the mutant we introduce. More precisely, the error code affects the mutant behavior and the mutant affects the error code behavior at the same time. We also define a new mutation testing matrix, relevancy mutation score, to see if the commit change is tested well. Relevant mutation score is the ratio of killed relevant mutants among the total number of the relevant mutants. Imagine that we have thousands of mutants. If we can rank and the mutants and pick up few mutants to measure the test suit quality to test the effect of the code change, it will be very useful and practical to apply mutation testing in continuous regression. The test suit can be refined in a good way by targeting killing a subset of mutants. To reach the objective, we propose a method MuDelta to find a small set of mutants. The figure shows the overview of our work. We extract the features and labels from the historical commit to train the learning model, and then the model is used to predict the priority of mutants. For the learner, we choose using XGBoost. It is very important to decide what feature we use for the machine learning model. We need to consider three parts: the change, the link, and the mutant. The features about the change, the link, and the mutant compose the feature of MuDelta. We can consider three different types of feature: contextual feature, mutant utility feature proposed by the previous work, predicting fault relevant mutants, and the mutant modification feature. First, we construct a program control and data dependency graph by using a cheaper static analysis. Then we leverage the graph analysis, extract the features about the node connection and cluster characteristics. The set of features describe the contextual feature, mutant utility feature are from the previous work that are designed to predict fault relevant mutants. The set of features can describe the mutant characteristics itself. Mutant modification interaction feature describe the deep feature and the feature linked between the change and the mutants. We use the commit dataset with 50 commits from software Coreutils. The figure shows the timeline of the commit. We split the data to three parts: training, validation, and testing. The red commits are used to train and validation, and the blue commits are only used for testing. We have three research questions. First, we study the model performance and also compare MuDelta with the other method. Next, we study how the mutant from MuDelta compare with the mutant set from the baselines with respect to the commit relevant mutation score. Last but not least, we study the fault resolution with the commit relevant mutants using the CoBench. The two figures shows the training and testing curves of MuDelta. The left figure shows the training curve. We use the matrix precision recall curve and ROC curve. The dataset is imbalanced, and ROC may give misleading conclusion, so that it is necessary to consider both of precision and recall. We can see that the model in the end converge. The right figure is the performance of the model on the test data. The dashed line are the random baseline. PR curve area is about 0.5, and ROC area is about 0.8 for our model, which both are much higher than the random baseline. We also tried the other models from the ensemble models to the new network. The table shows the compare result for ROC area, precision, and recall area, MCC calculation. XGBoost has the highest values. For the new network, MLP and the mixed MLP are inspired from the other work, deep fault location. Mixed MLP have multiple group input. We use grid search to find the best parameters for the model. We can see that XGBoost is the best. To answer the second research question, we compare three type mutant set from MuDelta, random, and modification respectively. The box plot demonstrates that the subsuming relevant mutation score when we target to kill the selected mutants from the three set by randomly generate the test cases. X-axis is the top K mutant we use, Y-axis is the subsuming relevant mutation score. The simulation is repeated by multiple times. We can see that only use mutant from the modification or random lead to the various mutation score. Targeting killing the top K mutant from MuDelta give higher subsuming relevant mutation score. We also compute the test effect size to see if MuDelta is more efficient than other method. 0.5 means the two techniques have no difference. The pink bars are about MuDelta and random. The green bars are about MuDelta and modification. We can see that MuDelta is more effective than the random and modification. To answer research question 3, we use the dataset co-bunch and analyze top 100 mutants from MuDelta, random, and modification. Then we see if the test kills the mutant and also find the fault. We repeat the experiments from multiple times. The figure shows the box plot values of APFD of the three methods: MuDelta, random, and modification. APFD means average percentage of fault detected. We can see that MuDelta has a higher APFD values. Thanks for listening. Now you can ask me any questions. Thanks.
Hello.
Okay.
Nobody ask any question?
So first, I would like to thank everyone for this interesting paper, especially you, Wei, who has done most of the work. Mark tells me here on backstage, but both of the authors should have credit. So I will please use the chat to add questions. My first questions really is what you find. So during this commit time, right? You're really trying to minimize use of the mutants. So it's really sort of sharp when you select, and that would be a reduction of time. Have I understood that correctly?
Yeah. And I think there is one question from the Guzu, I think. Do I need to retrain the classification? Oh yeah, I think it depends on your data. For example, if you have enough training data set and your training data set is more diverse and representative, it means a lot of patterns of the commit and changes. You don't need to retrain the model. You only need to retrain the model once and apply and deploy the model in practice, and you can prioritize and select the importance mutant. But for example, if you change the language, for example, sure, if you're different project language, Python or Java or C or C++, you should train the model for each one, because it really depends on the specific field. So for example, for the Java, maybe you use the p-test. In our study, we use the MART. It's about C mutation tool, mutate the LVM level For Java, if you mutate the source code level, so of course it depends on your training data set. If your training data set is very good and strong, you only need one time. But if your training data set is less, and you should consider the incremental training. So next time you don't need to retrain the model from scratch. You just continue training. And there are many tricks. Transfer learning, and it's a machine learning method. So I think it's not difficult to solve the issue. Yeah.
Okay. So another question here on your data set here in the paper. I'm looking at the paper right now. It really says that of course the result is really based on your test subjects. So do you think you have have you done any further investigation in that, of doing sort of other test contracts or other pipelines, or have you, because in our CI/CD loop we have really huge sets of commits that goes in every time. So you have only trained with what I understood is kind of small commits or small changes.
Yeah, I see. Yeah. For the data set, actually, I spent most 6 months to collect the data set, and the main difficulty is to get the ground truth about the relevant mutants. So spend a lot of time to label the data. So actually, we collect 5,000 commit from Coreutils, and we remove some non-meaningful commit, and because the data set from our previous work, commit-aware mutation testing, is published in Ecosemi, and the paper describe how we collect the data and what the criteria. Yeah, sure. The commit is less. It's better to give huge data for the training model. So I think this is the main difficulty for the mutation testing, to build a very good benchmark data set for mutation testing. It really costs a lot of time. So yeah, and for each commit, we spend 2 weeks to get the ground truth label, and we run multiple times to make sure the label are corrected, and also we use symbolic execution to generate test to target the page, because we dynamically run the program to label the random mutants. So we really need a very strong test suite. So it contains a lot of work, and yeah.
So was that the hardest part, you think, to in your paper, in your work, to create this sort of semantic symbolic execution of the mutants, or what is your most difficult work, would you say, when looking back? What took you the longest?
The longest is to because our study project, the C program, so we need annotate the C program, annotate the commit in the program to measure the pre and post commit. And also for the C program, usually the test cases are right in the bash script. They put everything to one script, so we need to manually or automatically write some script to split the test to some small test script to run. And I think more interesting is that in our work, there is one question we want to maybe in the future we can discuss. In which scenario in software engineering we can apply deep learning model? Because if you see in software engineering, many people apply deep learning model to extract the features of the code. Actually, in our work, we also tried, but it doesn't work. So it's very tricky. In which scenario we should apply deep learning, we should not apply deep learning, or which question or which field? So I think in our study, you can find the method we tried in our website. So yeah.
But if you talk about the different learning method, reinforcement learning is sort of also a more live approach where you sort of you start it off, but then you train and then you say, okay, this might be better and that. So wouldn't that be the approach?
Yeah, for the reinforcement learning, I also tried because for reinforcement learning, you need a model your problem. What you need to define the state and the transfer between the state. And the question is that when I tried the reinforcement learning for one commit, it can learn fast. But if I apply the model from this commit to the other commit, and the performance is not very good. So I mean, yeah.
I think this is a huge area, though, that we not only want to automate, and we also want to minimize the bugs. So it's really important work you have done, and I think there is a lot of followers that gonna sort of try out. So could you give any advice to people who wants to sort of replicate your work in their own environment?
You mean replicate my experience?
If they want to replicate your work and trying to do the similar in their own commit to reduce the mutants and so on, could you give any advice to these people?
Yeah, sure. I mean, if you want to use the same exactly the approach from our work, I can release the source code and I build everything in the Docker. So, but if you want to apply for the Java or Python program, I think
no, it doesn't work. No, it has to be C. I agree. So it was really LLVM Clang, right? Or
we studied the question in the LLVM level in the intermediate representation.
That's SIL. Okay, got you. Well, I don't have any more questions. Are there any more questions in the audience? Please put in the chat. Otherwise, I really would like to thank all of the authors. It was a very interesting paper, and you actually can take a few minutes break before the next video. It's a really interesting session here on mutation testing. If you don't have anything else around. So let's give the applause.
Thanks for listening. Thanks for interest.
And the next video will start